We've built up, over the past few chapters, a fairly complete understanding of how single particles behave in quantum mechanics. We can describe them with wave functions like psi of x, y, z, functions of position, which we can use to calculate expected values of, for instance, of what the x-coordinate will be. We know how to calculate the allowed set of energies for bound states, for instance, of the hydrogen atom, and we can predict the spectra. This is very nice and it's very useful, but it's of course not the end of the road for quantum mechanics. The next step that we're going to make is to talk about multiple particle systems, to start building things that are more complicated than a single particle in a single potential. The first step, then, is to expand on our formalism of wave functions to two-particle systems. If we're working with a one-particle wave function, psi of x, y, and z, if we're working with two particles, we no longer have the position of just one particle, x, y, and z. We're working with two particles, so the wave function psi is going to be a function of 6 variables, x1, y1, z1, and x2, y2, and z2. This means if we construct, for instance, a probability density for finding the particle at a particular position, we're not finding the particle. There are two particles, there are two positions, and what we get is a joint probability distribution for the position of both particles. So this is if we're talking about two particles, and you can easily imagine what would happen if we had more particles. You would have simply more arguments. This is part of what makes quantum mechanics so difficult to compute with, since effectively representing functions of many variables in the computer is a very difficult proposition. If our wave functions are functions of multiple variables, you might expect that our Hamiltonians would get more complicated as well, and they do. The Hamiltonian operator, which we had before, was simply, in the single particle case, was a momentum operator and a potential operator. Now you'll have to deal with the momentum of each particle separately. So for instance, the Hamiltonian for a particle might look like minus h bar squared over 2m times, and I'll write this as gradient squared with a subscript 1, minus h bar squared over 2m gradient squared with a subscript 2, where the gradient with a subscript 1 refers to partial derivatives with respect to x1, y1, and z1, and the subscript 2 refers to partial derivatives with respect to x2, y2, and z2. Essentially, this is the momentum of particle 1 in operator formalism with wave functions, and this is the momentum of particle 2. The potential energy now, of course, will also have to be a function of the positions of both of these particles, so we'll have to add on a potential term which is a function of both r1 vector and r2 vector. There are some simplifications that you can make. If the potential is only a function of the separation of the particles, for instance, you can do the same sort of thing as you can do in the case of the two-body problem in classical physics. Namely, instead of working with two independent bodies, work with the center of mass and the essentially angular orientation of the bodies about the center of mass. But that's a story for another day. The Hamiltonian we get here is now a partial differential equation in multiple variables, many more variables than we were working with originally. So it's much harder to work with. Our wave functions, of course, still have to be normalized, since we still have to represent, probability densities with them. But the normalizations we're going to work with are a little different. In particular, while the probability density that we're working with is still going to be psi star psi, we're going to have to integrate it over many, many dimensions. 6 dimensions in this case if I'm working with two particles in 3 dimensions, dx1, dy1, dz1, dx2, dy2, dz2. So if you're trying to normalize a wave function for two particles in 3 dimensions in Cartesian coordinates, you've got a lot of integrating to do. The time-independent Schrödinger equation is going to look very similar. Essentially, h psi equals e psi, same as before, where the Hamiltonian now is an operator h hat. The solutions you get to the time-independent Schrödinger equation are still going to behave the same way they behaved before, and this is the very comforting thing. When we derive the time-independent Schrödinger equation from the time-dependent Schrödinger equation, we still get the same sort of behavior. Our wave function now is a function of the positions of two particles, if I represent them as vectors r1 and r2, as the spatial part, the solution to the time-independent Schrödinger equation, and the time dependence looks very much the same, minus I e t over h bar. the same sort of expression as we got before. So adding multiple particles adds a great deal of complexity to the spatial part of the wave function, but if we have a stationary state, the temporal evolution is as simple as it was before. The subtle point of multiple particle wave functions comes from whether the particles are distinguishable or indistinguishable. Consider combining two one-dimensional systems. So the position of particle 1 is represented by x1, position of particle 2 represented by x2. So we have two particles in a one-dimensional system essentially, and the positions of those particles are independent. This looks a lot like two independent variables. So you can think about this as, in 2 dimensions, an x1 axis and an x2 axis. If I measure the positions of these particles at the same time, I illuminate the system with high energy radiation and look for where the radiation has scattered off of the positions of the particles. I can represent the outcome of a measurement by a point in this two-dimensional space. Suppose this point is 1, 0.3. I might also measure the particles to be here. Another possible outcome for this measurement is 0.3, 1. What I mean by whether the particles are indistinguishable or distinguishable is whether these two outcomes, 0.31 or 1, 0.3, are actually distinct. If I was measuring this in a two-dimensional space, these points would, of course, be very distinct. But I don't actually have a two-dimensional space. I have a one-dimensional space with two particles in it. So if I measure, say, this outcome in one-dimensional space, I'm measuring one particle at point 0.3 and another particle at position 1. So my wave function then essentially has a particle there and a particle there. If I measure this other outcome, 1, 0.3, one of my particles is at position 1, one of my particles is at position 0.3, so my wave function essentially looks like that. These guys are essentially the same. What does that mean? Well, if this is particle A and this is particle B, and this is particle A and this is particle B, then these two outcomes are different. But that requires the particles themselves to be distinguishable. And if the particles are not distinguishable, if this is an electron and this is an electron, there is no difference in principle between the electrons in these two peaks, then, well, electron-electron and electron-electron are actually the same outcome. And whether or not you count these as different is, well, one of the nuances of quantum mechanics. The essential fact that you have to keep in mind is that in quantum mechanics, the particles that we're working with, electrons, protons, photons, whatever they may be, are in principle indistinguishable. The wave function, quantum mechanics tells us, is all we can in principle know about these particles. So you can't paint one of them red or put a little piece of tape on it or do whatever you might do with other objects in order to keep track of whether or not they've exchanged places, for example. Particles are indistinguishable. Indistinguishable is a painfully long word, but essentially what this means is that we can't tell which particle is which. So let's consider what effect this has on quantum mechanics. If you had particles that were distinguishable, particle 1, its position being represented by the coordinate x1, could be in some wave function, in some state, psi sub a. And this would be, quantum mechanically, a complete description, all of the information necessary about particle 1. Likewise for particle 2, indexed by coordinate x2, in state psi sub b. The combined wave function for the overall state, then, is going to be psi as a function of x1 and x2. And we can write that down if particle 1 is in state psi a and particle 2 is in state psi b as simply the product psi a of x1 times psi b of x2. This gives us the sort of expression that you would expect to get for distinguishable particles. Namely, for instance, if I want to calculate the expected value of x1 for a particle in this state, this is the expected position of particle 1. My combined wave function here, calculating the expected value in this combined wave function, will require two integrals, one dx1 and one integral dx2. Both integrals are going to go from minus infinity to infinity. And the integrand, as before, is going to be psi star psi. If I expand that out, psi a star of x1, psi b star of x2, x1, and psi a x1, psi b of x2. This is the integrand you would get. Psi star and psi combined together with a multiplication means that's our probability density for position And this is then, of course, the expected value of position formula that we're familiar with from single particle quantum mechanics. Looking at what's a function of what here, we can simplify things a little bit. I have functions of x1, and I have functions of x2. If I pull the terms that are not functions of x2 out of the x2 integral, essentially moving them over here, what I end up with is two integrals that you probably recognize. Integral from minus infinity to infinity dx1 of psi sub a star of x1, psi sub a of x1 for my first integral, and the integral from minus infinity to infinity of, with respect to x2, of psi b star of x2, psi b of x2. So these integrals essentially separate out, and this is a normalization integral for psi sub b. If psi sub b is normalized, this is going to go to 1. And this expression on the left, the integral with respect to x1, is the single particle expectation value of the position x1 for a particle in the state A. So essentially, if I have distinguishable particles, my result looks pretty much as expected. These particles are clearly distinguishable because if the expected value of the position of the particle were different for state B as for state A, well, I got the expected value for state A, not some combination involving the expected value for state B. So these particles are clearly distinguishable, and there's nothing in principle wrong with writing wave functions like this, except for the fact that the fundamental particles we're working with are not distinguishable. So we have to somehow encode the indistinguishability of particles into our formulation of quantum mechanics. So how do we write a wave function for indistinguishable particles? The key fact is what happens if we exchange the particles. The wave function for particle 1, particle 2 versus the wave function for particle 2, particle 1. Exchanging the positions at which we evaluate coordinates is essentially, if you think back to that plot I was making earlier of x1 and x2, it's implying a degree of symmetry between this point and this point. That my wave function must be equal here and here, essentially being equal somehow across the axis. This sort of line here where x1 equals x2. That degree of symmetry implies some constraints on allowable forms of the wave function. We don't need just that the wave function itself doesn't change if I exchange x1 and x2. What we need is for the observables not to change, and furthermore, we need the observables not to change at all if we swap the particles back to where they were originally. So if we want the exchange of particles to not matter, let's define an exchange operator, p hat. Now don't worry, we're not going to be working with p hat in the context of it as a mathematical operator, but it's a useful notation to use. What we need in order for the wave function essentially to not change the observables is for p hat acting on psi, x1, x2, which is more or less defined to be psi of x2, x1. We need that to be equal to plus or minus psi of x1, x2. You know the way to not change the observables in quantum mechanics is to multiply by a complex phase, and this plus or minus essentially takes care of that complex phase. You could imagine any arbitrary e to the I phi being multiplied by psi, and that would not change the observables, but the fact that applying the exchange operator twice gets us back where we started means that the phase that we multiply by has to be either 0 or pi, meaning we have to either go from plus psi to minus psi or from plus psi to plus psi. Either we don't change the wave function at all by exchanging operands, or we flip the sign of the wave function by exchanging the particles. This is sort of a law of physics. The indistinguishability of particles requires this to hold. If I exchange the order of the arguments of a two-particle wave function, I must get my original wave function back with a plus or a minus sign. This symmetrization or antisymmetrization under exchanging the arguments, symmetry referring to the plus sign, antisymmetry referring to the minus sign, has some remarkable consequences, which we'll talk about over the next couple of lectures. One way, however, to write down these wave functions, since that's what we're going to want to do in the end, is if I have the two single particle states that I was working with in the past slide, psi A, psi B. My wave function, psi of x1, x2, started off as psi sub A of x1, psi sub B of x2. This was the distinguishable particle wave function, and it turns out that if I combine this with a permutation of x1 and x2, for instance, psi A of x2 instead of psi A of x1, and then psi B of x1 instead of x2, if I combine these two pieces with either a plus sign or a minus sign, I get something that obeys the requirement that the particles are indistinguishable from the perspective of quantum mechanics. If I'm going to properly normalize this, I'll need a normalization constant out front. And for instance, you can check this fairly easily. If I wanted to know what psi of x2, x1 was here, well, it's going to be this expression on the right, exchanging 2's for 1's and 1's for 2's. So it's going to give me A, psi A of x2, psi B of x1, plus or minus psi A of x1, psi B of x2. If you compare the expression I get after exchanging these particles with the expression I got before exchanging these particles, you can see here's psi A x1, psi B x2, A1, B2, whereas here's A2, B1, A2, B1. So these expressions are essentially the same, except the plus or minus sign is going to mess things up a little bit. If I use the plus sign, clearly these two expressions are the same. A1, B2 plus A2, B1 versus A2, B1 plus A1, B2. All I've done is exchange the order of these two terms. Since this is just multiplication, we're working with wave functions, there's nothing fancy about the order of the terms over addition. Everything commutes, that's fine. If I use the minus sign, I have A1, B2 and minus A1, B2 in my exchanged version, whereas minus A2, B1 becomes plus A2, B1 in my exchanged version. So I flip the signs in my wave function if I use the minus sign when I calculate my exchanged form. So this trick for making indistinguishable particle wave functions from distinguishable particle wave functions actually always works. You need to combine all of the different permutations of all of your particles with appropriate plus or minus signs such that you obey this overall antisymmetry under exchange or symmetry under exchange requirement. Whether or not we have symmetry or antisymmetry under exchange is a really interesting topic. And it gets us down to a distinction that I've mentioned earlier on in the context of fermions and bosons. Essentially, indistinguishability has a couple of consequences. First of all, if I have the plus version, the symmetry under exchange, essentially psi of x2, x1 equals psi of x1, x2. My exchanged version is equal to my original version. This is the case for bosons. And bosons were the particles that we talked about earlier that had spin, integer spin, 0, 1, or 2, etc. If you make the other choice, say psi of x2, x1 is equal to minus psi of x1, x2, that's the case for fermions. And fermions, we said earlier, were particles with half-integer spin. Spin 1/2, 3/2, 5/2, etc., on up to infinity. There's actually quite a lot that you can do with this. For instance, the symmetry and antisymmetry properties of these wave functions have, well, it has observable effects, and the behavior of fermions and bosons is crucially different in a lot of ways that have very important consequences. For instance, earlier on we talked a little bit about superfluid helium in the context of the domain of quantum mechanics and whether that was important or not. Helium atoms are bosons with integer spin, and they have very different behavior than other liquid gases, for instance. If you wanted to determine the quantum mechanical behavior of very cold liquid hydrogen, for instance, it would behave differently. Hydrogen behaves differently from helium in that context. The indistinguishability of particles is something of an axiom in quantum mechanics. the exchange can't affect anything. In particular, it doesn't affect the Hamiltonian. Exchanging two particles should not affect the energy of the state if the particles are completely indistinguishable. Put another way, the exchange operator and the Hamiltonian operator commute. The commutator of p hat and h hat is 0. What that means is that we can always write wave functions in these forms. x2, x1 after exchange equal to plus or minus psi of x1, x2. We can do that and still be able to come up with stationary states. We can come up with a simultaneous set of eigenstates, a set of simultaneous eigenstates of both this exchange operator and the Hamiltonian. So it's always possible to write our wave functions like this. This is similar to the reasoning we applied earlier when we were talking about functions, or about the time-independent Schrödinger equation in one dimension with an even potential. You could always write the solution as either even or odd if the potential was even in one dimension. You can make a similar argument, or this is a very similar argument. There is a symmetry property that we can exploit when we're looking for solutions of multiple particle wave functions. So bosons and fermions and exchange, these are fundamental properties of nature, and the connection between the spin of the particle and the symmetry or antisymmetry of the wave function overall is a really interesting topic that we'll discuss a little more later on. One application that you guys have hopefully heard about from your chemistry class is the Pauli exclusion principle. The Pauli exclusion principle holds for fermions, and for fermions we know that the exchange operator acting on the wave function psi gives you minus the wave function psi. So suppose the wave function that we were working with was writable in the form that we were talking about earlier. Psi of x1, x2 is equal to some normalization constant times psi a, x1, psi b, x2. Now we're using the minus sign since we're talking about fermions. We're talking about exchange antisymmetric spatial wave functions. Psi a, x2, psi b, x1 for our second term as before. The Pauli exclusion principle determines what happens if the two particles are in the same state. If the two particles are in the same state, psi a is equal to psi b. What that means is that I can rewrite this as psi a and rewrite this as psi a. You can tell what we're left with now. We've got psi a x1, psi a x2 minus psi a x2, psi a x1. We've got essentially something minus itself. So if the particles are in the same state, then psi of x1, x2 equals 0 with this particular fermion antisymmetry under exchange. This is interesting, and I suppose I shouldn't use an exclamation point here because 0 factorial is 1, and that wouldn't be all that interesting. But what this means is that this is not possible. First of all, the wave function psi equals 0 is a perfectly valid solution to the Schrödinger equation, but it doesn't tell you anything, so this is not useful. It does not describe a normalizable state. What this means, and what the Pauli exclusion principle says, is that two fermions cannot occupy the same state. I'm not quite sure how I spelled occupy there, but I don't think it was right. Two fermions cannot occupy the same quantum mechanical state, and that comes from the fact that fermions are required to obey antisymmetry under exchange. And of course, if you have two particles in the same state, exchanging things doesn't do anything. It's not going to change your wave function. So if it's not going to change your wave function, and yet it is going to change your wave function by giving it a minus sign, you've got a problem. Two fermions cannot occupy the same quantum mechanical state as a result, and this comes just from the nature of indistinguishable particles the antisymmetric combination to render two otherwise distinguishable particles indistinguishable means that those two particles cannot occupy the same state. For bosons, though, we use the plus sign, so that's no problem. If we use a plus sign here, we end up with psi ax1, psi ax2 plus psi ax2, psi ax1. So just twice psi ax1, psi bx2. Or sorry, psi ax2. So that's a perfectly valid wave function. Bosons, if we use the plus sign, make the symmetric instead of antisymmetric combination to render the particles indistinguishable. Those particles can occupy the same state right off the bat. This ability to put multiple particles into the same quantum mechanical state is the difference between the bizarre behavior of liquid helium and the behavior of liquid hydrogen. As an example, consider back to the very beginning. The very first quantum mechanical system we worked with was a particle in a box. What happens if we put two particles in a box? Well, two particles in a box, if we're going to write wave functions as symmetric or antisymmetric combinations of our distinguishable single particle wave functions, is a little bit of a lie. Because if these particles are anything that we know of realistically, those particles will interact, and the interaction in the Hamiltonian will affect the potential. So we won't be working with a simple v of x equals 0 inside the box and infinity outside the box potential. We'll be working with something more complicated, and accounting for that interaction will mean that our stationary states are not simply the stationary states of single particles. But suppose, for instance, vigorously waving my hands, though you can't really see it in a video lecture, suppose those particles didn't actually interact, then the potential would not be affected and the stationary states would indeed be the single particle stationary states. If I have distinguishable particles then, I can write down my states as, for instance, psi nm of x1, x2 as, well, the product of the state for n and the state for m. Psi sub n of x1, psi sub m of x2. The ground state, for instance, and I'm going to smush this down, give myself some space. The ground state then has n and m both equal to 1. In this case, looks like my normalization overall out front, 2 over a, different normalization since I've got the product of two separately normalized functions, times sine of pi x1 over a, sine of pi x2 over a. And it has energy, if I substitute 1 for the energy of one particle and 1 for the energy of the other particle, I'm just going to get k plus k. My total energy is 2k. The first excited state, and there are two ways I can do this. I could write psi 2,1 or psi 1,2, depending on which particle I bump up from the ground state, is going to be very similar. It's going to be 2 over a sine pi x1 over a sine 2 pi x2 over a, if, for instance, I use this combination. So there are actually two distinct ways to write the first excited state. One where I put the 2 with the x1, and the other where I put the 2 with the x2. That means this first excited state, for this distinguishable particles case, is doubly degenerate. There are two allowable states with the same energy. That's what we mean when we say degeneracy. Suppose instead of distinguishable particles, I had bosons. The states that I would work with then would look very similar. If I had psi 1,1, my ground state, well, there's nothing wrong with putting two quantum mechanical particles in the same quantum state with bosons. So I'd have to make the symmetric indistinguishabilization. Sure, why not? I'll make up a word. The symmetric form of this, sine of pi x1, sine of pi x2, plus sine of pi x2, sine of pi x1, but since they're the same, that's all just going to end up adding up. So your ground state is essentially going to be unchanged from your distinguishable particle case. If your distinguishable particles are in the same quantum state, are they really all that distinguishable? So psi 1,1 is unchanged. The first excited state, however, that looks a little different. Psi 1, 2, for instance. Let me actually not write it as psi 1, 2. Let me write it as psi first excited. And that's going to be a symmetric under exchange version of the distinguishable particle wave function here, such that the particles are rendered indistinguishable. What it ends up looking like is root 2 over a times sine of pi x1 over a sine 2 pi x2 over a plus sine 2 pi x1 over a sine pi x2 over a. So I've moved the 2 from the term with x2 to the term with x1. And if you calculate observables with this first excited state, you'll get a different result than if you had two distinguishable particles. For instance, if I calculate the expected position of particle 1 or particle 2, I'll get the same answer, which is a requirement if the particles are going to be distinguishable. One thing to notice about this is that if I try to swap which of x1 or x2 has the 2, it doesn't work. I get the same quantum mechanical state back. So this is non-degenerate. There is only one allowed quantum mechanical state for the first excited state for bosons. Degeneracy does have consequences in the physical world. So the fact that distinguishable particles and non-distinguishable particles have different degeneracies for the first excited state means that, well, it means we're onto something. There should be some observable consequences for this prediction. The last possibility, fermions. Well, what about the ground state, psi 1, 1? The Pauli exclusion principle tells us that no two fermions can occupy the same quantum mechanical state. And in fact, if you look at our psi 1, 1 state here and try to make an antisymmetric under interchange version of it by adding on essentially another term that looks exactly like this, or more accurately, subtracting off a term that looks exactly like this, you get 0. So the ground state doesn't exist. There's no psi 1, 1 under these circumstances. Our new ground state, then, is essentially our first excited state from before, but with a minus sign. And I'll indulge in a little copy pasting here, just to save myself the writing. The only difference here is that we have a minus sign to render the two states antisymmetric under exchange, and we're combining two terms such that the resulting state is a valid state for indistinguishable particles. So our ground state again, which corresponded to our first excited state before, is also non-degenerate. There's only one allowable state here for our ground state, only one quantum mechanical state. And, well, fermions, bosons, and distinguishable particles obviously behave very differently here. Fermions and bosons differ in the sense that the ground state is different. Indistinguishable particles and distinguishable particles differ in the sense of the degeneracy of whether or not of the states. So there's a lot of interesting phenomena here, and it all boils down to this fundamental fact that quantum mechanical particles are indistinguishable. There is no difference between two electrons. Any two electrons are essentially exactly the same. They obey the same laws of physics. There is no additional information here that would allow us to keep track of which electron is which. We can make quantum mechanics validate this approach, we make quantum mechanics fail to keep track of which particle is which by making these symmetric or antisymmetric combinations of what would otherwise be distinguishable particle wave functions. And lo and behold, the distinguishable particles, bosons and fermions, all behave differently. So there's a lot going on here. To check your understanding, just to drive home the complexity of multiparticle wave functions, I'd like you to write down the normalization integral for a three-particle wave function in three-dimensional space. Finally, reflect on what it means for two fermions to be non-interacting if they can't occupy the same quantum mechanical state. Those two particles in a box that I did on the last slide, for a fermion they couldn't exist in the same state, but I wrote down the ground state, I wrote down the stationary states from which I was constructing those antisymmetric and symmetric combinations by stating that the particles didn't interact. So what does it mean for two things that don't interact to exclude each other from doing something? And finally, what I've been talking about in the context of the particle in a box is just the spatial wave function. We're just talking about psi of x, for instance, or in the case of two particles, psi of x1, x2. How would that change if I included spin? Particle 1 and particle 2 will now have independent spins, which you can think of as extra arguments to your wave function. So how might the inclusion of spin affect this symmetrization or antisymmetrization? These are things to reflect on. And if you've got these down, I think you've got the basics of multiparticle quantum mechanics soundly in your mind. We've built up, over the past few chapters, a fairly complete understanding of how single particles behave in quantum mechanics. We can describe them with wave functions, like psi of x, y, z, functions of position, which we can use to calculate expected values of, for instance, of what the x-coordinate will be. We know how to calculate the allowed set of energies for bound states, for instance, of the hydrogen atom, and we can predict the spectra. This is very nice and it's very useful, but it's of course not the end of the road for quantum mechanics. The next step that we're going to make is to talk about multiple particle systems, to start building things that are more complicated than a single particle in a single potential. The first step, then, is to expand on our formalism of wave functions to two-particle systems. If we're working with a one-part x2, y2, and z2, essentially this is the momentum of particle 1 in operator formalism with wave functions, and this is the momentum of particle 2. The potential energy now, of course, will also have to be a function of the positions of both of these particles, so we'll have to add on a potential term which is a function of both r1 vector and r2 vector. There are some simplifications that you can make. If the potential is only a function of the separation of the particles, for instance, you can do the same sort of thing as you can do in the case of the two-body problem in classical physics. Namely, instead of working with two independent bodies, work with the center of mass and the essentially angular orientation of the bodies about the center of mass. But that's a story for another day. The Hamiltonian we get here is now a partial differential equation in particle wave function, psi of x, y, and z. If we're working with two particles, we no longer have the position of just one particle, x, y, and z. We're working with two particles, so the wave function psi is going to be a function of 6 variables, x1, y1, z1, and x2, y2, and z2. This means if we construct, for instance, a probability density for finding the particle at a particular position, we're not finding the particle. There are two particles. There are two positions. And what we get is a joint probability distribution for the position of both particles. So this is if we're talking about two particles, and you can easily imagine what would happen if we had more particles. You would have simply more arguments. This is part of what makes quantum mechanics so difficult to compute with, since effectively multiple variables, many more variables than we were working with originally. So it's much harder to work with. Our wave functions, of course, still have to be normalized, since we still have to represent, probability densities with them. But the normalizations we're going to work with are a little different. In particular, while the probability density that we're working with is still going to be psi star psi, we're going to have to integrate it over many, many dimensions. 6 dimensions in this case if I'm working with two particles in 3 dimensions, dx1, dy1, dz1, dx2, dy2, dz2. So if you're trying to normalize a wave function for two particles in 3 dimensions in Cartesian coordinates, you've got a lot of integrating to do. The time-independent Schrödinger representing functions of many variables in the computer is a very difficult proposition. If our wave functions are functions of multiple variables, you might expect that our Hamiltonians would get more complicated as well, and they do. The Hamiltonian operator, which we had before, was simply, in the single particle case, was a momentum operator and a potential operator. Now you'll have to deal with the momentum of each particle separately. So for instance, the Hamiltonian for a particle might look like minus h bar squared over 2m times, and I'll write this as gradient squared with a subscript 1, minus h bar squared over 2m gradient squared with a subscript 2. where the gradient with the subscript 1 refers to partial derivatives with respect to x1, y1, and z1, and the subscript 2 refers to partial derivatives with respect to